Come on. Come on, work. I think we're live.
Really? Yes. Is there any audio?
Is there? I hear it.
Oh, yay. The chat exploded, which seems promising. Yay. Hi, guys. Woo. Here I've been just reading your questions and not being able to answer them fast enough, but
Yeah.
now I can't even ask. It's going to be even harder to answer.
Yeah, this is going to be a little nuts.
Okay, so hi, Nick.
Hi, Diana. Long time no see.
Yeah, except for the past half hour where we've been staring at each other going, what is going on? What did you do? What did you finally do to
I went back into the stream settings on YouTube and I refreshed them.
Oh, that's it? Just refreshing? Dude,
And so
to restart a meeting refreshing. It's like that thing, like, did you turn it off and on? It always applies. I wonder if there's a joke about the universe, like turning it off and on right now, because there's a lot of things going wrong.
Yes. Oh. So here we are. We're live.
We both made it.
Audio and everything. Everybody can hear us?
Yeah, it seems like it.
Okay.
So
yeah, this is
take it away.
Yeah. So I guess I don't know. There's people here that know you, and there's people here that know me. So
yeah, that's true. Well, this is your channel, so I'm
right.
suspecting most people know who you are more than me.
So yeah. So I wanted to do. I wanted to do a live stream, have some fun with everybody, and now that we're like, half an hour later than we're supposed to, we should be able to get this thing started. For those of you who don't know me, I'm Nick Lucid. I do stuff on this channel, the Science Asylum, where I play, I'm a crazy guy. But I do a lot of different videos, but my expertise is in relativity, general relativity, which I'm excited to have started a series on recently.
Nice.
Very exciting.
And what took you so long? I feel like that's been your expertise for a while now.
It is, but I think when it's that close to you, it just you want to do it right, and then you're afraid you can't. Mm-hmm. And so I think I just put it off.
I think that's why, interestingly, there's a topic that's near and dear to me, which is the struggles that women have to face. It's the only time I'm going to talk about this in this live stream, I promise. The struggles that women have had to face in the sciences, and it's something that I really care about, so I don't talk a lot about, because it's like you got to do it the right way.
Right.
Because there are real struggles, and then there are not real struggles. And so like really talking about them the right way, I think, is important. Anyways.
Yeah. And so I think with general relativity, it was a matter of me feeling confident in it, I guess. I kind of had imposter syndrome for a while. And having the ability to do the animations that I want, I have a certain way I want it to look. And if I can't get it to look that way, then I'm just not going to do it. And so I've only recently felt like I had developed the skills for it.
Yeah. It's like it's easier to marry off your least favorite child.
Right.
Just like that. You don't have any kids, right?
I do not.
Yeah, me neither. Obviously.
Right.
I just have Lego scientists.
I have a niece.
Oh, that's cute. I have 6 nephews and 1 niece.
Yep.
The rest of my siblings got busier than I have been able to.
Sure. I think I'm going to enjoy being an uncle. It's going to be fun.
A new niece.
Yeah, she's a year and a half, maybe.
Oh, nice. So it's
Yeah.
it's a good time to start introducing her to that general relativity series.
Right. Yeah. You know, got to start them while they're young.
So how are the questions going to work for this? By the way, I'm Diana. Nick hasn't introduced me, but
sorry. Yeah. So this is Diana. If you don't know her,
I do the
where are
channel
your interests?
Oh, I'm my interests. Well, physics, obviously. Oh, specifically in physics?
Yes.
Within physics, I think fluid dynamics is one of my favorite topics, but I think that's been since making videos, because there's just some really visually stunning and fascinating fluid dynamics experiments. In general, I'm a big fan of astrophysics. Looking up at the stars, that's what got me really into science and physics originally. And then particle physics is kind of cool because you get to smash things. And optics, oh, I think that was my favorite in college, because we got to make holograms and learn how holograms work and lasers. And I think there's something really fascinating about electricity and magnetism, and then as it relates to waves through light.
Sure.
Yeah,
I took optics in undergrad, and I had a teacher that really cared about students, and he wanted them to learn, but he was used to, like, he was older, and so he was used to, you know, back in the day when, you know, students in a classroom would be more interactive and everything. And so when no one would, you know, he'd ask a question and no one would answer, and he would just move on, and he started to have trouble, like, staying focused, and he kind of developed this reputation for being a bad teacher. But he wasn't. I mean, he cared, you know. And so one time I went to his office hours, and no one ever goes to anyone's office hours. But I went to his office hours, and I had a conversation with him. You know, I was like, I don't really understand what's going on here, you know. And we had a conversation, and it was so much better. And so then I realized that, like, he just needs to like interface with people.
Yeah.
And so I just started, like, answering his questions in class and asking questions in class. And, you know, people would give me these weird looks. So they turn around and be like, what are you doing? But then the lectures were so much better.
That's crazy. I feel like that's one of the hard things. This is like a lesson that can be generalized to a lot of professors, which is that they're really good at learning science and then doing science, and then they're thrown into teaching. And there's such an expertise that comes over time, or that maybe people will never be that into. But yeah, it's interesting that, like, that you, as the student, you found his trick. I wonder if he carried that on into other classes. Hopefully. There was a question that went by, which is, how long did you study? And you went on to do some postgraduate work. I stopped at my undergrad. I did my undergrad in physics at MIT, and then did a little bit of research afterwards in astrophysics, and then started moving on. And I was actually applying to grad school. I was doing the I think I told you this, maybe.
GRE.
Yeah, I was doing the GRE, and I took the general one, and then I was like, I don't want to study for the physics GRE. And that's the reason I didn't go to grad school, was because I was over it. I was over studying anymore. There's some regrets I have from not going to grad school, but, like, I ended up doing this. It eventually led on to this, so I can't complain.
Right. Yeah, I did a master's.
Yes, that's what I thought.
And so I had to take the general GRE, but I didn't have to take the physics one, because the place I applied didn't require it. And I was like, well, I'm not going to take it then, because I don't want to take that test.
I think maybe I was aiming too high. I was like, I was looking at a lot of schools that required it. I should have aimed lower.
I didn't go to a big school, so it wasn't.
Or not aimed lower. I think it's more like aimed smarter, because the colleges that are not using the GRE now are starting to recognize that it doesn't actually in any way correlate to your success as a scientist. Like your skills doing research, your skills taking classes, they don't correlate. Your success doesn't correlate in grad school with the GRE scores that you had. So
yeah, and I went to grad school, the same place I went to undergrad, so it wasn't like everybody knew me, and they were just like, just take the general GRE and we'll just approve it. It'll be fine.
That's nice. Good luck, Maxie, who's studying for the GRE now.
Oh yeah, good luck. It's not as bad as it sounds going in. I had issues with it because it was timed, and I don't do well on time tests.
Yeah. What, dude, there are too many questions.
I know, they're zipping by really fast. I guess we should probably stop reminiscing and take some of these questions. They've waited long enough. Let's see. We can scooch it. If you scooch the chat up off the bottom a little bit, it'll stop scrolling.
Oh, that's nice. Are you guys chess nerds? I like that question. I never got into chess. I love games. Do you play any games, Nick?
I never got like real big into chess. I mean, I learned to play it. And I wanted to get big into it. And I got like, this, I actually, when I was high school, I collected this. I collected a bunch of like pewter pieces and like a marble chessboard and everything. And I wanted it to be this like cool thing. I still have the chessboard. But I don't ever play it. It's not out. I don't have a lot of room in my home to put it out. But
how big of a chessboard is it?
It's normal sized. It's not huge.
Yeah, but they take up table space.
They do.
You can't like mount it on the wall and play.
Right.
Unless you have magnets, I guess. That'd be kind of a cool. I wonder if that would change people's strategy or affect how they play if you had to play sideways on a wall.
That'd be right. I mean, you'd have to take like, would you be on the sides or on the top and the bottom?
I don't know. I feel like sides. I don't know.
Yeah, sides might be more fair.
Are there any? Let's see. What is your favorite quantum mechanics interpretation?
Oh boy.
I don't have an answer to that question.
Well, I don't know if I have a favorite. I have interpretations that I have issues with. And okay, so there are a lot that have been ruled out by this point. A lot fewer than were around in like 1926. There's only a few left, but I know everybody gets obsessed with pilot wave model. And I just can't get into it because I can't let go of locality. I just can't do it.
This is over my head, and I'm going to tell you why. Because as an undergrad, you could do physics where you take like the 3 quantum mechanics classes, or you could do physics where you do a focus in something else. I did that and took the 1 quantum mechanics class, and then I focused in electrical engineering. So I can talk to you a whole lot more about capacitors and transistors.
Yeah, I did
about quantum mechanics, but I'm great at asking questions. So let me ask you this: I didn't know that there were like a lot of interpretations of quantum mechanics. And here's where I slip into my expertise, which is being curious. I didn't know that there were a lot of quantum mechanics interpretations in the 20s that are now gone. Tell us about that, Nick.
Okay. I guess a little conversation about this. So, quantum mechanics is based on just a bunch of probability math, right? And
yes.
So there's this quantum wave function, which I did a video about it a few months ago, but basically the idea is there are these interpretations where you have to be able to look at I mean, this is something we do in all physics, right? You want to look at numbers that you've calculated using models, and you want to be able to say something about the universe.
Right. And typically you want to be able to do a test.
Right.
And then rule out theories.
Right. And so we would like to be able to do that in quantum mechanics as well. And so when we get some kind of number, some probability, we want to be able to like look at that number and be like, well, this says this about the system. And the problem is when you're working with probability and statistics, there's a lot of different interpretations. There's a lot of ways you can like, well, what does this number actually mean? And so back in the day, back in the 1920s, when we first were developing this, we had a huge list of possible interpretations. Some people thought that this was, the fact that only probabilities worked on a quantum level meant that it was some new thing that we didn't understand, and we couldn't understand. It was just weird. And then other people were like, no, it's fine. It's just showing our lack of knowledge. It doesn't mean that the universe is weird. And so that this argument began. And so, the question comes down to like, well, what is the quantum wave function? And we still don't know. There are some that we've ruled out. We've ruled out a lot of what we call hidden variable interpretations.
Right.
And so those are ones where like, well, no, those properties, the particles have those properties. We just can't measure them for whatever reason.
Yeah. And people were clever enough to come up with like, was it Bell's?
Bell, yeah. Joseph Bell, I think.
God, my memory is so bad. But yeah, people have come up with the most creative ways to rule out different theories on quantum mechanics. So I find this fascinating in and of itself, that like just the concept of interpretations, that you have like quantum mechanics, which is a set of I don't know, mathematical rules and principles that describe how the quantum world, the very, very small world, works. But then there are interpretations of that, which I find to be a fascinating concept in and of itself, that like we have had to interpret what all that math means, because we can't conceive of it. Like we have to interpret it. We have to like, it's almost like a translation. It is like an interpreter, like a translator into like concepts that we can understand, which is why there's interpretations like the many worlds, or many, I think that's what it's called, many universes,
many worlds
or something like that, where like you open Schrodinger's cat, the box that Schrodinger's cat is in, and the cat's either alive or dead, but that interpretation says that it's not actually alive or dead when you open it. You actually create another universe where in one universe the cat is alive and the other cat is dead. And the thing is, interpretations like that are ruled out by doing tests.
Right.
That seems like a hard one to test if there's a second universe created in which you cannot wander and go test because you're in your own universe. So I don't know that I have a favorite interpretation. I have a least favorite, which is that one.
Right. I don't like it either.
Not a fan, but it's still around because people are still
well, because you can't rule it out.
But as a non-quantum physicist, as somebody who's not at the level where like people are still duking it out, like physicists are still coming up with ways to experiment and coming up with new theories, and those are people who have done a whole lot more studying and have gone a lot further in physics and specifically in quantum mechanics. So they still are coming up with ways, new theories and ways. So like how am I supposed to come up with a favorite interpretation besides just like what sounds nice to me?
Right. I think that's really the sort of the spirit of the question, though. What feels right to you?
Well, certainly not. Yeah, Sean Carroll, certainly not that one. Here's a nice question. Dianna and Nick. Dianna has two N's, by the way. That's the only time I'll be sassy, I promise. I'm thinking of becoming an astrophysicist or astronomer. I'm afraid I won't get a job after grad school. Shout out to Anne. Anne with 2 N's. Is it a risky degree and job to have?
Yeah, it's tough to say. Because I mean, it depends
an
on
astrophysicist or astronomer. Yeah. The thing is, like, if you're aiming to become an astrophysicist or astronomer, it's certainly not a risky degree. It's the degree that you want in order to be an astrophysicist or astronomer. If you want to go on and do something else, a lot of the skills are really, what's the word I'm looking for? Commutative? Like, you can use them elsewhere.
right.
A lot of the skills are transferable. Well, that seems like a good word.
That's a better word.
To a lot of other fields, like you can go on into software engineering very easily because you have to learn programming in a lot of the classes you do. And if you're at a school where you don't learn software engineering, shame on that school, because you have to learn to code for a lot of science and tech jobs nowadays. Yeah, that's my answer.
I think it depends on, what you're going for. Cause I know people who went and they got a degree because they thought it was gonna, get them a good job. And then they were miserable the entire time they were going through. And then they're like, I don't even want a job in this. And so when I was going through undergrad, particularly, I made sure that I was doing something that I was enjoying, so that if for whatever reason I didn't get a job in physics, I still kind of enjoyed the ride. That's not something I guess you want to do if you're doing a PhD. You kind of want to have a plan in place.
Yeah. What is your favorite computer language? Have you done much programming, Nick?
Yeah. So I majored in computer science before I switched to physics.
Oh, snap.
So I have a background, I guess you could say. But I did a lot of programming in high school.
Oh, that's cool. Yeah, you got a head start.
Yeah, and so like there was QBasic, which is the thing that everybody should start. Well, everybody did start on back in the day. I don't know if anyone uses it anymore. And then that went on, like that was sophomore year, and then junior year was C++, and then senior year was Java. And so like I learned a lot of these things. And then later on, like as an adult, I learned a lot of HTML and Python, and it's kind of just a hobby now.
Yeah.
But I love Python. It's so easy.
That's what I was gonna say. That's what I learned on. I learned on Python when I got to college. I think I was a sophomore, junior at MIT, and the intro classes were in Python. And then a lot of the intro. By the way, shout out to OpenCourseWare at MIT. They have a lot of their classes just online and available, which are awesome. And as a student there, we used OpenCourseWare all the time, which I didn't expect. Like we would take our normal classes and then we'd go onto the website where they had old classes available and learn from those. If there was ever a teacher, kind of like you were talking about, Nick, where they weren't great in lecture, we'd go back to some of the old lectures or lecture notes. I love this question. Why does time seem to flow in one direction? I have no idea. Do you have an answer for that?
I have a kind of a half answer, I guess. I don't know enough about this to be absolutely sure, but I understand that there are some quantum phenomena that go the other way. That it is possible in quantum mechanics for things to go the other way through time. It just doesn't seem that that's how things work on like a normal scale.
On a macro scale, yeah.
Yeah, and I'm not sure where the disconnect is or how that happens, but judging from that, all I can take from that is that, well, it just appears to be the arrow of time. It doesn't like it's not actually really there.
Yeah. Well, I've heard of that too, these quantum mechanical processes that go backwards. My question is, why can't I, like, when somebody asks a question about time, why don't I remember those factoids like you did? I'm impressed. I'm like, oh yeah, no, I know about those processes. it's probably actually what's his face? Alan Guth. There's a physics professor I used to have a lot of chats with about the nature of reality and time. He was a cosmologist. He is still a cosmologist. He's still with us.
Okay.
He came up with inflation theory, which is like a theory right after the Big Bang, where there was this period of really, really intense expansion. And the theory explains a lot of our observations. But again, we were talking about testing. There's not great ways to test it, although there are some. There was a. Do you remember this like bicep 2 experiment where we thought we saw polarization in the light from
the CMB?
Yeah, from the CMB.
Yeah, I remember this.
Oh, this is a quick little detour of a story. There was bicep 2 is the name of an experiment carried out down in, I think, Antarctica, where there's a lot less light pollution and stuff. And they were looking at light from the cosmic microwave background, like the very first light that ever was able to travel through the universe, when the universe cooled down enough for light to start traveling across. And we supposedly were seeing polarization, meaning like the direction that the light waves were pointed were all aligned in certain places around the sky, which would indicate, I don't know the details of the theory, but supposedly this would support inflation theory. I'm guessing that means like if we saw polarization of light from one direction, the same as another direction in two parts of the sky that haven't had enough time to talk to each other, then there had to have been this period of intense inflation. So that's what they thought they saw, but in fact, it was dust in, I don't know if it was in the galaxy or like the intergalactic medium, but it was dust impacting the direction of light, which is really, really sad.
Bummer. It's doing the astrophysics is hard because
it is.
I know I was reading about like when we're trying to measure the sizes of galaxies, we have to know how far away they are so that we can judge from the brightness, like an average, how many stars are there. And so if we can't properly judge the distance, then we don't know how big they are. And so like sometimes we'll think, oh, well, there's this impossibly large galaxy or an impossibly small galaxy. And then it turns out we just had the distance wrong and it's actually normal.
Yeah. Dude, I read an article the other day that was like about adjusting the size of the I don't know why I said I read the article. I read the headline of an article. Yes, I too can be one of those people from time to time. But the point of it was that it was adjusting the size of the Milky Way galaxy. And we thought for a long time it was 100,000 light years across. And now I think that it was saying, I don't know, you guys can Google this, fact check. I think it was something like a factor of 1.5. Like it's now we're thinking that it's 150,000 light years across. Don't quote me, Google it before you share that information with anyone else. My point is, if that's the case, 150,000 light years versus 100,000 light years, like that is our own galaxy. And that's a difference of 50,000 light years. That's 50,000 years that light would have to travel, and light travels really goddamn fast. Sorry, that was intense. Really damn fast. Really, really fast. So that's a big error. Like if you're like, I'm gonna make a mug, but I'm gonna get my width of my mug off by 50,000 light years, you're gonna run out of material halfway through the handle. It's crazy. Yeah, those are the scales of astrophysical measurements.
And it's difficult. I got a question that I think it says, what was someone had said that Feynman mentioned that antiparticles travel back in time, and what's the deal with that? Not really. They do in Feynman diagrams, right? So Feynman diagrams are basically space-time diagrams. They're from relativity, and in order to make those work properly, you have to draw antiparticles as if they're going back in time. It's just sort of like the notation. But not even Richard Feynman thought the particles were actually going back in time. He didn't think that that was a valid interpretation of his diagrams. Now, it might turn out in the future that they do, that they're actually just particles traveling backwards in time, but I mean, that's certainly consistent with some of the symmetries we see in quantum mechanics, I think. But I don't think most particle physicists don't actually think that that's a legitimate thing.
I'm getting summoned to my next meeting. I'm trying to push it back a little bit.
You booked me back to back with somebody?
Yeah, I mean, it's been back to back. We actually have a video coming out hopefully tomorrow. So there's a lot going on. This is well, it's always busy time, but yeah, so I'm trying to push that one back a little bit. So we can keep talking for a couple more minutes, but I do have to
have to go.
Yeah, pretty soon.
Bummer.
Let's take a couple like really quick questions.
Yes.
Somebody asked oh, this one. Why is it the particles without an electric charge have a spin? I suspect it's because overall they have no charge. Well, I actually don't know how to answer that. The thing about particles with charge is that they are made of smaller particles that do have fractions of charge. So there's that to take into consideration as well.
So I guess like what the question is, how can particles without charge have spin?
Yes.
I think
they're two different properties.
Right. They're separate things.
Yeah, it's like how can a particle without charge have, wait. I was trying to think of a specific particle. How can a particle with momentum have no mass?
Right.
Like a photon.
They're separate things. Now, a lot of times we measure spin as a magnetic moment, and so it's not going to have a magnetic moment without a charge.
Yes.
Well, I mean, neutrons do, because like you said, they're made of smaller particles that do have charge. But like elementary particles, like neutrinos, have a spin, and they don't have a magnetic moment because they're not charged. And so I don't think there's no reason why they wouldn't, be able to have spin.
Yeah. Let's see. What else have you studied instead? I'm not sure what that was referring to. None of these are quick questions. Y'all are asking for essays.
Let's see. What does a photon see? It doesn't see anything.
It sees no time.
Right. Everything measured in what you might call a photon's frame of reference. I hate saying that because it doesn't really have one, but everything along a path that a photon would take in space-time has zero length, and it's one of the weirdest things in relativity. And I will do a video on this in much more detail.
That's awesome. You should also do a video about this one. How do the exchange of bosons cause force? This is something that vexed me for a very long time. I kept asking, like, okay, so you've got this, people, when I was getting my physics degree, people would talk about force carriers. So like they talk about a proton and an electron. So those attract each other, or an electron and electron, those repel each other. And a photon is exchanged between the two, and that's the carrier of the force between the two. And so the analogy some professors gave me was like, okay, so you imagine that an electron is repelling an electron, it exchanges a photon, it bumps into it, and like they repel. I'm like, okay, so that breaks down if you've got a photon and an electron where they're attracting each other. So I think the better way to think about it, which which starts to get into like where you have to interpret and you can't wrap your head around the reality of things. But the better way to think about it is of everything, all of the forces and charges being fields that permeate all of space. And then there are particles that travel through the fields, and they are peaks in the field. Ugh.
Yeah, I've been trying to read quantum field theory textbook because I never took a class on it, and so I'm trying to teach myself, and it's so hard.
The intuition is what's hard. I think like there's like it's kind of like you can wrap your head around what these physicists are saying and what they've measured, but the intuition for that being how the world works for me is where it breaks down in my brain.
And I have issues with the notation. Like if I'm looking at a mathematical equation, I want to be able to look at it and be like, okay, this is saying this in English. And I can't do that with QFT. I just, it's so alien.
Okay. Maybe two more quick questions.
Okay.
I can answer this one. Where did antimatter go after the Big Bang? The answer is that we don't know. That is one of the biggest unanswered questions that the largest lab in the world, which is CERN, the Large Hadron Collider, is looking into. It's one of the big unanswered questions. Like, we don't know. There should be a balanced amount of antimatter and matter in the world, but like most of the things that we see, it's all matter. It's regular matter. So we don't know yet. I love those questions where it's like, we don't know. Moving on.
Right. There's one that says, why do photons lose energy when they travel through space?
That one is interesting. So it has to do with with the fact that like as space expands, the photons get stretched out, and so the light wave gets stretched out, and wavelengths that are longer have lower energy. So on these cosmic scales, energy is not conserved.
Yes. And this is the topic we were talking about. What was it a month or two ago?
Yeah, about how the stretching of space leads to the stretching of light waves, which is actually quite a complicated.
It is. It's wild.
Okay, I should go.
Okay.
Thanks for having me on your channel, Nick.
Yeah, maybe we can do this again sometime.
Yeah,
with no technical difficulties.
We know now to just restart everything.
Right.
Restart the universe. Thanks, everybody. I mean, if you want to keep going, you don't let me stop you guys.
Yeah, well, we'll see. I usually go an hour on these, but I might go another 10 minutes. We'll see.
Okay, cool. I unfortunately do have to.
Yeah, it's okay. I understand.
This video is currently at 17 and a half minutes. So there's a lot we got to do. Thank you for having me.
Yeah.
And
anytime.
Good luck in the quarantine times.
Yes, you too. And
bye.
See you later. All right. So let's see. Sorry about all the technical difficulties, but here we are. At least we got to talk to her for about 20 minutes. We got a lot of questions in here. Let's see what we got. Maybe I can answer some of these bigger ones before we go. What classes do you teach, Nick? I don't anymore, actually. I do this full time, the video stuff on my channel, and it's pretty awesome. But I used to teach. I used to teach college and university classes, mostly introductory physics, astronomy, that sort of thing. There's a hierarchy in higher education where like you're not allowed to teach higher level classes. Like even if you could, you're not allowed to unless you have, certain degree levels or like certain, job seniority or whatever. And so that can get complicated. Should you do a PhD? I don't think it's really up to you. I mean, I didn't want to, but there are some things that, require it if you want to be a professor or, a practicing scientist or something like that. Maybe, depending on your field, you might need a PhD, but I think that, that, it really comes down to what you want. And I can tell you it's a lot of stress and a lot of work. And so it needs to be worth it to you. You've got to have that vision of what you want out of your life. And if, you need the PhD to do that, then at least you'll have the motivation to get through. Let's see. Yeah, so sorry, Dianna had to leave. The plan was to have her here for an hour or so, and we got up to 5:00 because we couldn't get things to work. And I had like the entire chat calling me and her a boomer, but that's how it goes, I guess. We can't get technology to work. We are not boomers, just for the record. Let's see. She's, yeah. Let's see. Do relativity and quantum theories have a common theory? They do not. We do not have a model that puts both of them together. We have some attempts, but that's about it. Let's see. What do we got in here? Could you explain your path into physics and computer science? Sure. So at the beginning of the Q&A here, we were talking about our background. Oh, hold on. My battery's going to die. I'll be right back. All sorts of technical difficulties today. All right. So let's see. I actually started getting into computers when I was a kid. It was sort of an up and coming thing back then. And excuse me. And so, you get your whole family just kind of like pushing you into computer science and pushing you into it. And they always try to have like, a new computer around for me to play with. My parents did. And, so I got into it, and I was into it for a really long time. And then I think I did a tech support job at some point, like shortly after high school. And I hated it. I was miserable doing that. I wasn't stimulated enough, I guess. And then I kind of discovered astronomy and physics and switched majors in college. But I started college, a community college, with the intent of getting a computer science degree. Let's see. Wow, the number of watching people's going down. All the Dianna people have left. Let's see. Please, on sound waves, how is amplitude does not affect the speed? It's kind of a tricky question to answer in a live stream. Kind of need animations for sound. How do virtual photon exchanges cause attraction, right? So this goes back to what Dianna was saying about quantum fields and like what's happening with those. And it's kind of tough to say. There's not a lot of intuition with it, but it definitely. See, the thing is that virtual particles aren't necessarily real actual particles. They're just particle-like things, where a quantum field is doing some weird, fluctuation thing. and it looks kind of like a particle sometimes, but it's not really like a real particle. These virtual particles do not have to obey the laws of physics. And so they're generally considered to be not real things. And so the attraction happens because of like field energies and stuff, which I would really can't explain with words. But it's very non-intuitive. Let's see. Maybe one more question and we'll call it a day. This has been a rough live stream session. Let's see. It's a personal opinion here. Do I think the universe will expand forever? I'd hate to take a stance on that. I don't know. If you're going based on my feeling, I mean, I would have liked the universe to stop expanding and recollapse so that it would be this like, cyclical universe, almost kind of like a heartbeat or something. But it doesn't appear to be the case, right? If we look at data and the, cosmic background and that sort of stuff, we get numbers that don't seem to line up with a cyclical universe. They seem to line up with a very steadily increasing, probably accelerating universe. And so based on that, we have to conclude that the universe will expand forever. There really isn't much argument against it. All right, so let's see. Do physicists use relativistic mass? Not really. I actually had a conversation with Dr. Lincoln from Fermilab about this a little while back, and the idea is that like it's a really great educational tool. Like when you're first learning relativity, it's using something like relativistic mass. It helps connect the weirdness of relativity to things that you're more familiar with, like mass, right? We're familiar with what mass does, and so it does that, right? And it makes the transition into relativity and learning relativity pretty easy. Or I should say easier. I shouldn't say pretty easy. It depends on who you have as a teacher, I guess. But it makes it less stressful. But when you're talking an actual physicist, they don't use relativistic mass. In fact, they don't even use mass at all if you're talking about a particle physicist. Particle physicists, and it's really tough to say, particle physicists usually you just use energy instead, right? And so then we know that there's something called rest mass, and then there's all these other energies. And if you want to clump that all together and call it a relativistic mass, you can, but it's not all that useful for a physicist. Lots of emojis down here. Let's see. It's got a good question in here. Did I miss some near the beginning? Let's see, one more question. I want to make it a good one. I just got to pick one at this point, don't I? Do you miss doing any particular part of science, right? So versus research versus education versus tech or whatever. So we'll go with this one. And so I don't know that I miss it. I mean, when I was going through school, like Dianna did she said she did the specialization in like electrical engineering. Um, I made sure to pick the degree that had the fewest labs as possible. I hated doing labs. And so while I acknowledge that labs are very important, um, they're very important for, I should say lab experiments. Experiments are very important for science in general, particularly for physics. But I think that I never really liked it. And so I tried to do the more theoretical stuff. And I did enjoy doing research on Sun Mobile. I did my master's thesis on white dwarf stars. And yes, I say dwarf. I can't do dwarf. Like, how do you do that in one syllable? It just seems awkward to me. I did my thesis on those, and the research, it was kind of stressful, but like I did okay. And I still get to research now, even doing videos. I still get to research topics. You can't just put out a video, willy-nilly. You've got to be able to research it and fact check it and make sure that you're right, because, people are going to, that people have come to trust you, as a YouTube creator. They've come to trust me, and they've come to trust Dianna. And so we have to make sure we hold ourselves to a high standard there. And so I do get to research, but I don't miss experimental techie stuff at all. That was never my forte. All right. So I'm going to call it here, because like I said, this was meant to be, Dianna and I bouncing stuff off of each other, but maybe I can convince her to do this again. And hopefully we'll have fewer technical difficulties next time. At least that's the goal, right? Okay. So let's see here. And so on that note, I will see y'all later. Hopefully, at least some of you I will see in the comments, and we will hopefully get Dianna or some other physics creator to jump on this thing. So in that case, be safe in this troubling time, and have a good rest of your day.